Building a modern jet engine is one of the most punishing engineering challenges in existence. It requires blades that spin at 10,000 RPMs, in temperatures hotter than molten lava, without warping. Currently, only 4 nations possess the infrastructure to manufacture these systems from scratch. In 1986, India initiated a program to join that group. The government tasked the Gas Turbine Research Establishment to develop an indigenous power plant, the Cavari. The mandate was to create an afterburning turbofan capable of generating up to 90 kilonewtons of thrust. The goal was to provide the primary propulsion for India's new Tjas fighter jet. Success would have eliminated the country's reliance on foreign manufacturers for its frontline combat aircraft. However, the project began with a technology readiness level of only 2 or 3. It was supported by a $239 million budget, while global competitors typically spend billions to reach the same benchmarks. Geopolitical friction added to the difficulty. Following nuclear tests in 1998, international sanctions cut India off from the global aerospace materials and technical expertise needed to refine the design. Early prototypes struggled with specific mechanical shortfalls. The engine was overweight, failed to produce sufficient supersonic thrust, and the high-pressure turbines suffered repeated failures from thermal fatigue. In 2008, the Indian government officially removed the Cavari from the Tjas program, selecting American-made engines for the fighter instead. While the fighter engine project was sidelined, decades of testing provided a massive volume of data. It forced a complete reassessment of how India approached domestic engine design. Despite the public setbacks, research continued. Engineers moved the engine's maturity from a theoretical concept to a verified technology readiness level of 6. This effort resulted in 12 new type-certified aerospace alloys, capable of maintaining structural integrity under the extreme mechanical loads of a high-performance turbine. These breakthroughs were integrated into the Kabini core. This high-pressure gas generator serves as the heart of the engine, proving that the most complex elements of the propulsion cycle could be built indigenously. They also developed a full-authority digital engine control system, or FADC. This acts as the engine's brain, using software to manage fuel flow and performance parameters in real time. Mastering both the metallurgy and the digital control system meant India had successfully developed the components required to build a military-grade turbine. The hardware underwent rigorous validation, accumulating more than 2,550 hours of testing across multiple prototypes. To test performance at altitude, the engine was integrated into a modified Il-76 aircraft in Russia, completing 57 hours of flight trials. The progress was confirmed by an external audit from the French aerospace company Saffron, which cleared the engine for integration into a limited flight envelope. This audit officially verified the engine's airworthiness, marking a significant milestone for the decades of research. With a working core established, the project shifted focus. Engineers removed the fuel-heavy afterburner to create a non-afterburning version, known as the dry Cavari. This chart highlights the specific requirements for stealth drones like the Godidge. Because these platforms fly at subsonic speeds, they prioritize a small infrared signature and high fuel efficiency over the massive thrust needed for dogfighting. The dry Cavari generates approximately 50 kilonewtons of thrust. This provides the exact balance of power and low thermal output required for long-range, autonomous missions. The Cavari's specific performance profile, prioritizing efficiency over high supersonic thrust, met the exact requirements for an autonomous stealth platform. The technology also branched into naval warfare. Using the Kabini core as a base, researchers developed the Cavari marine gas turbine. In dockyard trials, this marine variant demonstrated the ability to generate 12 megawatts of power, providing a potential domestic propulsion option for the Navy's fleet. The program has also matured the domestic supply chain, enabling private companies like Godidge Aerospace to manufacture full engine modules at an industrial scale. The original Cavari program provided the technical data and industrial infrastructure India needed to begin developing its next generation of indigenous power plants. It remains the foundation for the upcoming Cavari 2.0 and the country's future stealth fleet.